Or when you're talking about gravitational field is really a study about gravitational forces, all right? Now, when you have masses tend to exert attractive forces on each other, okay? Meaning to say, if I have one mass m here and another mass m here, because of the nature of gravity, these masses will tend to exert some sort of attractive pull or attractive force on each other. This force is what we know as gravitational force, okay? Usually, gravitational force is significant if at least one of the masses is very large, all right? For example, like a planet like Earth, okay? For our case, like right now, if you're sitting at your table right now, your table has mass, you also have mass. By right, you both are exerting gravitational forces on each other. But then you don't really feel it as being significant because your masses are considered to be relatively small. But if you have a very large mass, let's just say like the Earth, because Earth has a very large mass, the gravitational force that it exerts on the table as well as you will be quite significant, okay, because the mass of the Earth is very large. All right. Now, there is something called gravitational field that you would need to know. Gravitational field is a definition question that will come up quite often. They will ask you to define what is a gravitational field. A gravitational field is just simply a region where a gravitational force is experienced by a mass. All right. So all masses tend to have their own gravitational field. For example, if I have a mass big M here, it tends to have its own gravitational field, such that if I go and place a mass inside the field, this mass will experience a gravitational force, Fg. Fg here stands for gravitational force, okay? So a gravitational field is just simply a region where gravitational force is experienced by a mass, all right? Now, we also have another term called gravitational field strength, all right? Now, gravitational field strength is just something that tells you how strong your field is. A higher gravitational field strength tends to cause a larger gravitational force for a given mass, okay? Now, when you're talking about gravitational field, you can normally represent gravitational field visually by using lines called field lines, all right? But when you draw your gravitational field using field lines, there are a few rules that you need to be aware of, okay? The first one is that field lines must always be perpendicular to your contacting surface, all right? So if I tell you, for example, you have a sphere with circular cross-sectional area and mass, and that sphere has mass m, the field around that sphere would look like this, okay? It will look like this pattern here. Because in the first place, your field lines must be perpendicular to your contacting surface. So the reason why your field lines looks like this right now is because it needs to maintain 90 degrees with your contacting surface. This one is what we call radial field line, okay? It seems to be radiating outwards from a point, all right? Now, another thing that you should also know is that when it comes to field lines, the spacing of the field lines actually tell you the field strength, is a measure of your field strength. The closer your lines are to each other, the stronger the field, and vice versa, all right? Meaning to say, the further apart your field, the further apart your lines, the weaker the field, all right? So if you look at the diagram that I just drew here, if you consider a case where I try to move away from the center, let's just say like this, away from the center, what can you say about the spacing of the field lines? You see, as I go further and further away, the spacing of your field lines is getting larger and larger and larger, right? So here I can say that away from the center, spacing line spacing increases. Therefore, field strength decreases. Okay, therefore field strength decreases here. The further away I go from the center, because the line spacing is getting larger and larger and larger, the field strength is considered to have decreased. Okay, the converse will also be true lah. If let's say I go towards the center like this, you notice that my line spacing becomes smaller. So this one here towards the center, line spacing decrease. This one I can just say that line spacing decrease. Therefore, field strength increases. Okay, so that is one thing to note here. And then the last thing that you need to be aware of is that field lines normally have a direction. Okay, so when you have direction, you need to draw something like an arrow to indicate the directions. So when you're talking about field lines, gravitational field lines specifically, gravitational field lines always point inwards towards the mass, because the direction of your field line is normally determined by the direction of force acting on the test mass placed in the field. How you determine the direction of your field is determined by the direction of a force acting on a test mass placed in the field. What we mean by that is that, for example, if I place a test mass M here, this mass, the red colored mass, will be attracted to the orange colored mass. This red mass will experience a gravitational force towards the center mass. So the direction of my gravitational force is inwards, right? So the direction of my field line will be inwards. Now, if I'm going to place the mass somewhere else, let's just say maybe diametrically opposite, right over here, the same result can also be seen. This red mass will be attracted towards the center mass. You experience a gravitational force. This is your test mass, okay? So since your direction of your gravitational force is inwards, it follows that the direction of your field must be inwards, okay? Right? So this is how we determine the direction of force on, this is how we determine the direction of your gravitational field, okay? So gravitational field, your lines will always have an arrow pointing inwards, okay? Now, field lines, sometimes they may ask you in your exam to define what are field lines, okay? Field lines can also be known as lines of force. If your question asks you to explain what is meant by field lines or line of force, you can just say that lines of force or field lines indicate the direction of force acting on a mass placed at a point in the field, okay? It's also correct to say it indicates the direction of acceleration acting on a mass placed on the field, because force is what causes acceleration in the first place. Both terms are interchangeable, all right? That is one thing to note. Okay, then next statement, the one below here, they tell you that for spherical mass like a planet, field lines are radial. This one I just explained to you. If you have a spherical mass, your lines tend to be radial because your lines have to maintain 90 degrees with your contacting surface, okay? And then your field strength tends to decrease with distance from the center as line separation increase. This one is what I mentioned. Now, one thing to note is this. There is something called point mass that you will eventually encounter, all right? Now, point mass is just a point where the whole mass is assumed to act, okay? Something like your center of mass that you learn in IGCSE or SPM, the point where the whole mass is assumed to act. So point mass here is just simply a point where the whole mass is assumed to act. So a point has no volume, no size. It's just a point. But for that point itself, you assume your mass is there, okay? Now, one of the questions that sometimes you will often encounter is this. They will tell you to explain why is it that for the field lines, when it comes to the field lines for a spherical mass, is identical to that of a point mass, right? So this one is one question that you see quite often later on. One of the questions they will ask you is, why is it that the field lines around a spherical mass can be assumed to be identical to that of a point mass? Now, when you're talking about a point mass, how are the field lines around a point mass like? If I tell you a point mass looks like this, the field lines around a point mass generally looks like this. It's also radial in pattern. Okay, it's also radial in pattern like this. Now, when you're talking about spherical mass has size, has volume. When you try to draw the field lines around it, it will look like this. Also radial because they're trying to maintain 90 degrees with your contacting surface. Now, for your case here, if you try to extrapolate the field lines around a spherical mass all the way into the mass itself, you will notice that it tends to terminate at a point. Okay, it appears to come from the center. Your field lines for a spherical mass tend to come from the center, appear to come from the center. This is your spherical mass. This one is your point mass. Okay, now for your point mass, you notice that your field lines all appear to come from the center, right? When it comes to a spherical mass, if you try to extrapolate the lines into the mass itself, you will notice that it tends to come from it appears to come from the center itself. It's because of this that we normally will be able to say that a spherical mass, the field line is identical to that of a point mass. Okay, that's why we have this statement here. Field lines or uniform spherical mass is identical to that of a point mass. All right, this one we will eventually go through it. Now, then the last statement here, the next statement I told you, the field lines are always perpendicular to the sphere, so the lines come from the center like a point mass. This is what I just explained. Okay, now another thing I should probably mention to you is this. Now, near the surface of the Earth, for small distances, field lines are approximately parallel and equal spacing to each other, thus gravitational field strength is constant. Now, what do I actually mean by that? If you consider, for example, maybe I should erase some stuff. Okay, maybe I'll just erase everything again. If let's say you consider the case where you have Earth, like this is say Earth, all right? Your field lines will always be radial. Okay, so it looks like this. Where it's always pointing inwards. Now, let's just consider a case where large distances are considered. Let's just say I consider large distances like this. Hey, wait. For example, I consider large distances. A large distance. When you look at very large distance away from the Earth, you can clearly see that the line spacing is changing, right? So here I can say that for very large distances, field line spacing changes. Therefore, field strength is not constant. Okay, so for very large distances away from the center of the Earth, I can see that the field line spacing is clearly changing, so the field strength is not constant. But some questions later on, eventually you encounter, they will ask you, what if I just consider a very small distance away, a relatively small distance? Say maybe I consider just a short distance like this. This one is relatively small distance now. Okay. This is relatively small distance. What if I just consider relatively small distance? Meaning to say I just look at just this small distance here, the length of the line that I just highlighted. Okay. Now, when it comes to a very small distance near the surface of the Earth, if you were to try and zoom in on the few lines there, what you'll see is that this is, say, the surface of your Earth. The few lines around your surface for that very small distance, this relatively small distance, your few lines will generally look like this. Okay, maybe you need to use a different color. Your few lines would generally look like this. Okay. So when you look at it like that for a very small distance, your few lines, you notice that they are about parallel to each other with almost equal line spacing. So here, we will say that the lines are approximately parallel in equal line spacing. Wait, let me just write this. This one, you can see that the lines are approximately parallel with equal line spacing. Therefore, field strength is constant. Okay, so for very, very small distances considered, we can consider your field strength to be constant because the lines are parallel and about equal line spacing, and they have about equal spacing. All right, so I can say that field lines are, I can say that the field strength is constant. But the moment I go and consider very, very large distances like this, for example, you see, if I happen to extrapolate the line like this, because they were radial in the first place, the larger the distance, the further apart the lines become, you see. So very, very large distance, you can see that if I were to consider this part and this part here, there's a very large difference in the line spacing. Therefore, the field strength cannot be considered to be constant. All right, so that's just one thing to note. Okay, so this is just talking about line spacing or field lines in general, how you look at the gravitational field visually. Now, what if you are interested in finding out the gravitational force acting on a particular mass? Now, for your case here, you want to find out the gravitational force acting on a particular mass. The gravitational force between the masses can actually be summarized by Newton's law. It's not related to Newton's first, second, or third law. It's an entirely new Newton's law. This one is called Newton's law of gravitational attraction, all right, which states that the force of attraction between 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of their separation. So meaning to say, if I have one mass, big M here, and one mass, small m here, if they are separated by a distance of r, the gravitational force between them will be, number one, proportional to the product of the masses. Number two, inversely proportional to the square of the separation. Now, if I wanted to combine these two together, I will end up with this expression where Fg is proportional to mm over r squared. Now, you know that in maths, when you want to get rid of this proportionality sign here, you have to introduce some sort of constant. So the constant that they've introduced here is called your universal gravitational constant G, with this value, 6.67 times 10 power minus 11. This value can be found from the datasheet in your exam paper. You don't need to remember this value. It will always be given inside your exam paper. All right. So if you introduce the constant G, capital G here, your gravitational force becomes Fg equals to Gmm over r squared. All right. So this one is the equation that you would use to find the gravitational force for a particular mass. Okay. Now in your AS, you might be thinking in AS, didn't you learn some sort of equation to find gravitational force before? In your AS, your gravitational force is known as your weight, right? So weight is equals to mg, your weight here being your gravitational force. So couldn't you use this equation also to find the force of gravity on a particular mass? This one, yes, you can use, all right? But this one comes with a certain condition. This equation cannot be used for, wait, how will I say this? This equation cannot be used. Okay, maybe I should rewrite this. This equation can only be used if G is known. Okay. Now, your G here is what you learn as free fall acceleration in AS. This one is also known as your gravitational field strength. Okay, this one is known as your gravitational field strength. Okay, this one is actually the next term I will be going through. But now I'm talking about gravitational force, right? So when you're talking about gravitational force, you might be thinking, can I use this also W equals to mg? So the thing I'll just mention is that yes, this equation can only be used if G is known. All right. And then after the next thing I'll just mention to you is that G is not equal to 9.81 or constant. Okay, maybe I don't make things complicated. G is not equals to 9.81 meter per second for very large distances away from the Earth. Okay, because sometimes some people have a tendency to use W equals to mg and G, they always assume it's 9.81 meter per second, carrying forward from your AS understanding. This one I'll just mention to you, when you're dealing with very, very large distances away from Earth, G is not equals to 9.81 meter per second squared. Because as I kind of explained to you already, when it comes to a spherical mass like Earth, where your field lines were radial in the first place, I mentioned to you that for very small distance, G is field strength is constant. Wait, for very small distance, field strength is constant. But then if you consider for very large distance, field strength is not constant. Okay, so for these very small distances here, field strength is constant. If you have a mass of say 3 kg here, wait, sorry, let me just. If you have a mass here, there's 3 kg, and a mass here, there's also 3 kg. This part here, you can actually just say that, since your field strength is constant, G would be equals to 9.81 meter per second squared. You can easily just say that the weight over here, or rather the gravitational force over here, is just mg, it's just 3 times 9.81. Okay, it doesn't matter whether you're here or here, because they're very small distance. relatively small distances, your G is assumed to be constant at 9.81 meter per second. This is what you were doing in your AS last time. In AS, you were moving your masses around, but your masses didn't move very, very large distances. So your G was always assumed to be constant at 9.81 for Earth. But now, when you're talking about this chapter for gravitational field, your masses are not considered to be a very small distance near the Earth. They are very large distances away, going all the way into outer space. So since your distance considered is very large, your field strength at that very large distance away will not be considered as constant. So if let's just say I have that same 3 kg mass, I place it over here, my G cannot be assumed to be 9.81 meter per second squared. This is wrong. It can only be assumed as 9.81 meter per second squared, very near to the surface of the Earth, but very far away cannot, because the field strength is no longer the same. So if I had done Fg equals to 3 times 9.81 here, this one will be wrong entirely, okay, because I cannot use that value of G. All right, so in cases like this, what I'll do is that I'll use this. Fg is equals to gmm over r squared. If I know the separation between the big mass and the small mass, and I know the value of both masses, I can actually find out the gravitational force between them accurately. Okay, right? So this is just one thing I should mention. Why is it that we don't use W equals to mg anymore? Okay, it's only if you know the value of G at that point. Okay, we cannot assume that G is 9.81 meter per second squared, because at very large distances, it's not constant in the first place. All right. Okay, now, another thing that I should probably mention to you is this. The Newton's law of gravitational attraction is only applicable for point masses, okay? Point mass, just now I explained to you, is just a point where masses is assumed to be, the whole mass is assumed to act, right? So the equation that you're seeing here is only applicable for 2-point masses, all right? But a lot of the questions that you see later on in your past year, they are not point mass. Instead, they are spheres, or instead they are spheres, not point mass. But then we still use the equation Fg equals to gmm over r squared. Now, the reason why we can still use this equation, even though it's only for point mass, is because when it comes to large objects with size or volume, we normally can approximate them to point masses. We can assume them to be point masses, provided they are either having very large separation or if they are perfectly spherical. Okay, if you have objects whose separation is very, very large, you can actually assume them to be point mass. Okay, example of that is something like this. For example, if you have this mass like this, and then another mass like this is your separation. This one cannot be considered as point mass. You cannot assume them as point mass. But if I have the same mass, but this time the separation is like this, maybe I use a different color. If the separation is like this one, then I can assume as point mass, okay? So the objects that I have can have size or volume then, but provided the separation is extremely large in relation to their size, I can actually assume them to be point masses, okay? So that's why you see later on in your questions, you can actually use this because the separation is considered to be very, very large. If they're very large in terms of separation, we can consider them as point mass. So from there, we can use this equation, all right? And then another thing that would also allow us to assume a large object as a point mass is if they are perfectly spherical, okay? So just now, I think I explained it a little to you already just now in the first page. I told you that the field lines for spherical mass is actually identical to that of a point mass. Because if you extrapolate the line for spherical mass, you will see that it tends to come from the center, just like that of a point mass. Okay, so if you see that your object is a sphere, you can also assume it to be a point mass. And then from there, you can actually apply Fg equals to gmm over r squared. All right, so that's one thing to know. Okay, and then another thing here would be that usually the masses that you're considering, the values will be different, all right? But the gravitational force of attraction between them, it will still be equal and opposite to each other as a result of Newton's third law. It could be that maybe this big mass that I have here is 3 times 10 power 24 kg, and then this mass here is maybe just 10 kg. I know that there are going to be gravitational forces exerted between them, but just because this mass has larger mass, it doesn't mean that one of the gravitational forces will be different. Okay, the forces would still be the same for both masses. Meaning to say, if this big mass exerts a gravitational force of say 50 Newton on the small mass m, the small mass m will also exert the same 50 Newton force on the big mass m, okay, due to Newton's third law, which tells you that when two bodies interact, they exert equal opposite forces on each other. Okay, so forces are equal regardless of the differences in the mass. All right, then we move on to the next term, gravitational field strength. Now, gravitational field strength, I explained to you a little just now. It tells you how strong your field is at a particular point. All right, it tells you the strength of your field at that point. A stronger field tends to produce a larger gravitational force for the same mass. All right, so gravitational field strength is denoted with the symbol G. It is actually defined as force acting per unit mass. G is Fg over m. And since just now you learned that gravitational force is gmm over r squared, you submit into this equation, G is gmm over r squared divided by m. The small m will cancel off, eventually giving you gravitational field strength as gm over r squared. When it comes to finding gravitational field strength, you actually have two different equations that you can use. You either use the first one on the left or the second one on the right. Now, which one would you use again depends on what is given to you in your question. All right. Now, if you look at both of the equations, you will notice that there are mass terms on both. But for the left one, the mass is at the bottom. For the right one, the mass is at the top. So one thing to note is just this now. For the first equation, where the mass is at the bottom, this one is usually referring to the test mass. Okay, the bottom mass is the less important mass, is the test mass. But then for the second equation, you see the mass is at the top. That one is actually your more important mass. It's usually the mass that produces the field itself. Okay, so you can just think of it as being something like this now visually. Your test mass, small m, is this one. This is your test mass. Your more important mass is the mass that produces the field. This is the big M. This is the mass producing the field. Okay, right? So these two, just be careful what mass terms are you using, right? If you're using the second one, the mass at the top is the mass producing the field, not the test mass. If you're using the first equation, where the mass is at the bottom, this is the less important mass. It is actually your test mass. Okay, right? So if let's say you're given this current diagram and you want to find the gravitational field strength at this point, if you know the mass that is placed at this point and you know the gravitational force, sorry, okay, let me just, sorry, my pen is acting up. Okay, for your diagram here that you have just now, if I ask you to find out the gravitational field strength at this point, how do I know which one I would use, whether it's the first one or second one? As I mentioned to you just now, it depends on what you're given in your question. So if I want to find the gravitational field strength at this point, if I know what was the mass that I placed here, the test mass that I placed here, and I know the gravitational force that was acting on that test mass, then I will just say G is Fg over m. Okay, if I know the test mass placed here and the gravitational force acting on it, I will just use G equals to Fg over m. All right. But if I do not know the gravitational force on the test mass, but I know the test mass and the mass producing the field, the value of the masses, and I know the separation between them, then I will just use G is Gm over R squared. Oh yeah, sorry. Actually, I don't need to know the test mass. If I don't know the gravitational force and I don't know the value of the test mass, and I don't know the gravitational force, but I know the point at which the test mass is placed, I know the separation, and I know the mass of the main mass, I will just use this. Okay, so it depends on what is given to you in your question. If you know the test mass and the gravitational force on it, use the first equation. You don't know the test mass, you don't know the gravitational force on it, but you know the separation and the mass of the main mass, then you use the second equation. Okay, so that's just one thing to note. Okay, field strength is a vector, it has an associated direction, and your unit is Newton per kg. You can actually find out why the unit is like that, because gravitational field strength is force over mass, right? So force as unit of Newton, mass as unit of kg, it will be Newton per kg. All right. And because field strength is a vector, eventually you will realize later on, when you want to add up two field strengths together, you need to consider the directions of the fields because they are vectors in the first place. But for this chapter, you won't really bother so much about adding them together. That one will be another different chapter.